If w equals h of r equals 4 raised to the power r minus 5, find r equals h inverse of w. I'm going to start with my exponential equation, w equals 4 to the r minus 5. I need to solve this for r. I can do so by switching from exponential form to logarithmic form. The base of my exponential is 4, so the base of my logarithm is going to be 4. The logarithm is equal to the exponent, so this is going to equal r minus 5. So I have log base 4 of w equals r minus 5. To solve for r, now I just need to add 5 to both sides of the equation. So log base 4 of w plus 5 equals r. So r equals h inverse of w equals log base 4 of w plus 5. Now I can verify that these two functions are inverses of one another graphically. Let's pull up our graphing calculator. In the y equals menu, I'm going to plot my exponential function first. Instead of r and w, I need to use x and y. On the graphing calculator, y is always a function of x. So I have 4 raised to the power, the quantity, need parentheses here, x minus 5. That looks okay. In y2, I'm going to put my log function, the inverse function here. I don't have log base 4 on the calculator, so I'm going to change this to a natural log. I'm thinking log base 4 of x plus 5. Log base 4 of x I can write as natural log of x divided by natural log of 4. So let's enter that. Natural log of x divided by natural log of 4. And then separately I have plus 5. That looks right. I'm going to enter y3 equals x because inverse functions are reflections about the line y equals x. Let's plot all three. So I have my linear function y equals x. This looks like an exponential function along here, and a log function along here. Let's look at some points here. Let's choose an input of, say, x equals 6 in my exponential function. I graphed the exponential function under y1. So I'm going to go into the trace mode. It says I'm on the first graph, so that should be my exponential. And I said I'm going to put in 6 for x. I get out 4 for y. Let's look at our exponential and make sure that this makes sense. If I input 6, my exponent is 6 minus 5, which is 1. 4 to the first power is indeed 4. This makes sense. If the 0.64 is on the exponential, then the 0.46 should be on the logarithmic function. Let's test this out. The logarithm I had plotted as y2. So let's switch to graph 2. Graph 3 puts me on the linear function. Graph 2, again looking for 2 in this upper right hand corner here. Now I should be on the log function. Now I'm putting in 4 for x. And as I expected, my y-coordinate is 6. Does that make sense in my function here? If I input 4, log base 4 of 4 is 1, because 4 to the first is 4. 1 plus 5 is 6. Yeah, it makes sense. My output is 6. Let's verify with another point. Let's go back to our exponential function, graph 1, and let's put in 4 for x. Y is 0.25, or 1/4. Does this make sense? Well, let's look. If I input 4 in my exponential function, my exponent is 4 minus 5, which is negative 1. 4 to the negative 1 is the same as 1/4. So this does make sense. If the point 4, 1/4, is on the exponential function, then the point 1/4, 4, should be on the log function. Let's go up to graph 2, the log function, and put in 1/4 for x. Indeed, as I expected, I get a y-coordinate of 4. We can verify that again with our formula. If I put in 1/4 as my input, log base 4 of 1/4, what am I thinking here? 4 raised to what power gives me 1/4? 4 to the negative 1 is 1/4. So negative 1 plus 5 is 4. So an output of 4 does indeed make sense. So at least with the two pairs of ordered pairs we've looked at, we do see that the x and y, or in our case, the r and w coordinates do reverse, as we expect in inverse functions. So for our function w equals h of r equals 4 to the r minus 5, we have the inverse r equals h inverse of w equals log base 4 of w plus 5.